Two advanced space probes are now orbiting the Sun. One from NASA, the other from Europe. They have begun studying our star up close, imaging the mechanisms of hot plasma and magnetic fields, even diving into its atmosphere, discovering new insights into the solar winds and the science of the stars. This is the Royal Observatory of Belgium in Brussels. Scientists have been studying the Sun from here for over 100 years, using telescopes like this. The observatory is also the World Data Centre for the Sunspot Index. It is now receiving data from the European Solar Orbiter, a wealth of information studying the Sun up close, well within the orbit of the planet Mercury. The imagery alone is spectacular, giving us a whole new perspective of our Sun and the nearest star.
It sometimes happens, I get into my office, I download the latest data and I stare for hours at it. It's so addictive actually. Nobody has ever seen the details of the corona in that much detail before. So every time we get an image down, it's the first time we see something at that scale, and that's really fascinating. It's really discovery space that we're entering.
I was personally blown away by the quality and degree of detail in these images. And clearly, as solar physicists, we've been looking at images of the Sun for many years. But by going 3 times closer, we can get the spatial resolution up by a factor of 3. And we see things that we haven't seen before. And that's, of course, the beauty of science, to explore the unexplored.
The journey of Solar Orbiter began in 2020 and has travelled over 2.5 billion kilometres, with gravity assists from Venus and Earth.
The spacecraft is performing very well, and we are very happy about that, because it is the first time that it had to go so close to the Sun, and so in this very challenging environment. And of course the spacecraft is designed for it, but this design is all based on modeling, on predictions, so you only really know that it's going to work until you have seen it working.
Solar Orbiter is basically a research mission, but ultimately we want to be able to predict space weather. These are energetic events that could have an impact on high-tech installations on Earth, GPS satellites, power grids. And we want to make sure that in the future we can predict geomagnetic storms based on solar activity. And for that we really need to take the Sun's temperature and measure the solar wind and connect the two. By going close to the Sun, we try to capture the physics of space weather events, and we want to film on the Sun the events that give rise to changes in the near-Earth environment. And we need to fly close to the Sun to be able to measure the solar wind while it's still in a pristine, undisturbed state.
One of the great mysteries of the Sun is the difference in temperature from its surface to its atmosphere, where it increases by 1 million degrees in a process that is not yet understood. Generation of the high-speed solar winds emanating from the star is another process under scrutiny.
For the mission, it's important in many ways, because on one hand, of course, the closer you go, the better resolution you get and the more details you can see. And it's also important because we want to understand the influence of the sun on planets, on the Earth. And for that, we want to come closer and we want to see what's happening and at the same time feel around the spacecraft how the environment is changing.
There's a way to make an entrance.
This is my destiny.
It was now a conspiracy of witches.
Download Veely today.
So the EUI, so the Extreme Ultraviolet Imager, sees the hot corona, so to speak, the atmosphere of the sun, at extremely high resolution, much higher than what we had before. And one of the problems that we are after is to understand why the corona is so hot. It's like 1,000,000 degrees or so, while the surface of the sun is 5,000, something like this. And that's really puzzling, and we're after that since decades. And we think that it's possibly because of tiny eruptions that go on all the time, but that are small, too small to be seen by other instruments. And now that with Orbiter we get so close to the sun, we can finally see them. And we did see a lot of them in the first images that we took. And the closer we get, the more we see. So we are really excited about this because we may finally be on the solution to that decade-long problem.
These measurements that the spacecraft is taken now and also later will be important to improve our understanding of the sun. One of the things we want to understand better is how the sun affects the Earth, but for that you have to really understand how the activity of the sun is caused, how it evolves, and when, for example, such a cloud of solar material leaves the sun, how it also propagates through space and goes towards the Earth. So for that we want to do several of those close passages to the sun to observe it from close by, and we also want to change the orbit of the spacecraft so that it can see the solar poles, because we have never ever seen those before, and they are important to understand the magnetic field of the sun.
The solar orbiter carries 10 instruments on board, imagers of various frequency, including an X-ray spectrometer and extreme ultraviolet imager, a magnetometer, energetic particle detector, and a solar wind analyzer suite. It also carries a radio and plasma wave suite, which measures electric and magnetic fields around the spacecraft.
So now the whole payload is working together. It's actually a lot of work to coordinate all that. But what that gives us is that we get a comprehensive diagnostics of the solar plasma, of the solar atmosphere. So we can, with EUI, get the dynamics, the fine scale structure, but then with other instruments like SPICE, we can get measurements of the temperature, of the density, these kind of things. So with all the instruments together, we get a comprehensive view and understanding of the physics. And then you have all the in situ instruments also that we are working with that will help us understand what the coronal mass ejections are and how they influence the physics of the heliosphere, which is the surroundings of the sun, so to speak.
By having all 10 instruments on Solar Orbiter operate together, we can really harness the entire power of this mission, which is designed to connect remote sensing observations of the sun, meaning pictures and spectra, and what you measure, essentially feeling the solar wind as it flies past the spacecraft. And for that we need all 10 instruments, and they've now all been tested and exercised and tuned like musical instruments. And so this is the first time we actually got all 10 working together as a team.
So this solar orbiter and the instruments on it, it's a new machine that we are bringing to a place in the space that has never been visited before. So when we do that, we cannot expect everything to work as it is designed or is expected. There is a steep learning curve to learn to operate the thing, and that's what we call commissioning phase. And we're now at the end of that phase, and we have learned how to operate our machine to the best of its capacities. and the results are actually fabulous.
It's important to have all the instruments working and operating in a coordinated way, because one of the main goals of the mission is to link the sun and its activity with the environment, and not only the environment close by, but also the planets. And for that we want to look at the sun's activity, at the solar activity, with many different telescopes that look at it in different wavelengths. So that means they are looking at different layers in the atmosphere, and they can also measure things like the magnetic field on the sun. And then at the same time, we also have instruments at the outside of the spacecraft that will sense and measure what's happening around the spacecraft itself. So whenever there is solar activity, we can feel the effects close to the spacecraft.
Among the things that we now see for the first time are really tiny sources of energy release in the corona. And we are now very curious to find out in what sense they are connected to the large-scale structure of the solar wind and the energy that gets essentially put into the flow of particles towards Earth. And we try to really use models to connect what we see on the surface to what we see in the wind. And that is something that clearly takes more time and investigation to really pinpoint where a solar wind package came from. But we believe that we've done quite well in terms of pointing at the right place, and thereby we hope to get this complete picture of cause and effect. Close approach of solar orbiter to the Sun, to about 1/3 of the distance between Sun and Earth, is so important because it allows us to get measurements of the solar wind in an almost pristine state before it gets mixed on its way to Earth. And more importantly, to combine these measurements with pictures of the Sun and spectra that we can then connect and get a complete picture of the Sun and solar wind.
Scientists are also studying the dangerous solar storms that affect Earth.
This first perihelion was clearly our first scientific milestone after getting all the instruments calibrated. So this really gives us good confidence that we'll be able to do this again, and we'll do it roughly twice a year when we fly by the Sun again. In between, we'll be far away from Earth, so that takes a lot of time to get the data downloaded. But in between these far away periods, we have also close by periods where we can dump all the data that we've accumulated, and then it's Christmas for the scientists to look at the data and get new scientific insights.
The Parker Solar Probe is the second spacecraft now operating close to the Sun. It was launched by NASA in 2018 and has taken 4 years and several gravity assists to reach its operational orbit. Its elliptical orbit bringing it closer and closer to the star's corona, a boundary layer not clearly understood. This project has been over 50 years in the making.
The fact that the Sun is hot has been a major technological challenge, and why it's taken us so long to fly Parker Solar Probe.
That design of the heat shield, where the front of the heat shield that faces the Sun is hot enough to melt aluminum, but the backside, where the spacecraft electronics and instruments are, is actually at room temperature. That's been the key to getting this mission done.
This is a dream come true. One of the major goals for the Parker Solar Probe mission is to fly through the solar corona, and we are doing that now.
The edge of the Sun's atmosphere is known as the Alphen critical surface, a postulated zone where the solar wind goes from a slow to extremely fast speed, spreading out through the solar system. The Parker Solar Probe has passed through this barrier into the corona, showing that the boundary is indeed lumpy, and has sampled material still bound to the Sun.
Two of the most challenging scientific mysteries in astrophysics occur in a region that we call the solar corona.
The instruments on board have shown that outside the boundary, the solar winds accelerate away from the sun at high speed, unable to fall back onto the surface. However, inside the boundary, the magnetic field is much stronger, and solar material is much slower, tied to the surface.
That we've always known that the atmosphere of the sun, the corona, spins with the sun, spins the same speed that the sun does. But out at the Earth, the solar wind is moving straight out from the sun, so it's no longer spinning. Where that transition happens is very important for understanding, because that spinning of the corona actually helps slow down the sun. All stars get slower in their spinning as they get older. Parker Solar Probe sees that that transition from spinning to straight happens further from the sun than we thought. And that actually has implications for every star in the universe and how they slow down. And that's important actually for the habitability of solar systems around distant stars.
Gaining knowledge of our sun will help us understand all the other stars around us. This will help us with the search for habitable exoplanets. Understanding the processes of the solar winds and energetic particles will assist with finding worlds that, like the Earth, have magnetic shielding to help protect living organisms on the planet's surface.
Parker Solar Probe is the first mission to get close enough to the sun to see where the action is actually happening, where the solar wind is accelerated, where the corona is getting heated. And we've seen a lot of new science that we don't completely understand, but there have been some remarkable results about small events that we can see in Parker Solar Probe that get smeared out in the 93 million miles between the Earth and the sun.
We are so excited for these new results coming down from Parker Solar Probe. Parker has gone closer to the sun than we've ever gone before. It's inside the orbit of Mercury. We're seeing the solar atmosphere as it emits its material out into the solar system. We call that the solar wind. And we're seeing this process up close and personal at a higher detail and complexity than we've ever seen before, actually as it's being formed. So we're able to study the solar wind and all of its variability and complexity up close like we just can't do from Earth.
The protective magnetic field surrounding Earth is constantly buffered by solar winds and energetic particles. At the poles, these solar disturbances create spectacular auroras. It may also cause the atmosphere to leak out into space.
So the sun not only has this constant solar wind that blows out in all directions, it has solar storms, solar flares, and coronal mass ejections. And those energetic storms can accelerate particles up to almost the speed of light. And those energetic particles can actually cause radiation sickness in astronauts if they're out unprotected when those happen. On the Earth, we're protected by the Earth's magnetic field and the atmosphere of the Earth. But once you're out in space, away from the Earth's magnetic field, those can be a danger to not only astronauts, but also spacecraft.
The sun is capable of energizing pieces of atoms up to really high speeds and energies, and these are damaging to astronauts and to electronics. Now, we're protected down here on Earth from these particles, but on the moon or beyond, astronauts wouldn't have that luxury. So one of the key missions of Parker Solar Probe is to understand how these particles are actually being accelerated so that we can better predict and protect against them.
Another phenomenon of our sun deals with space dust and debris, pieces that clump together by static electricity, and then, as they grow by gravity, there appears to be none close to the sun.
Space dust is pieces of comets and asteroid debris that fills our solar system, but close to the sun, they can be so hot that they actually vaporize, or that material can also be pushed away by the radiation of the sun. And so there ought to be a region around the sun where there is no dust. And for the first time, Parker Solar Probe is seeing evidence of this dust-free zone.
So the sun goes from a quiet period, what we call solar minimum, to solar maximum, and back again, about every 11 years. And we launched into a very quiet solar minimum. That's actually helping this mission, because during solar minimum, things are simple. There aren't very many sunspots. There aren't very many of these solar storms. What ones we're seeing are small, and that allows us to individually identify every single event.
And then later, as Parker continues to observe the sun, we'll see this ramp up of activity and energy bursts, and we'll be able to see the more complex and bigger energy bursts.
In the coming years, the probes will witness up close the power of the sun during its more active phase, as it spirals closer and faster to the star.
Parker Solar Probe is already the fastest human-made object. As it gets closer to the sun and spirals in and goes faster and faster, it will reach 500,000 miles an hour. So we are so excited to see the results as Parker continues on its mission.
Before Parker Solar Probe passed through the sun's Alphen boundary, it detected kinks in the solar wind, where it would momentarily double back on itself. Scientists call them solar wind switchbacks, but had no idea of the mechanism that caused them to form. As Parker got closer and closer to the sun, it detected more and more of these switchbacks. It was able to track one of them to its origin on the visible surface of the sun. On the surface, you can see defined cells as heat rose from beneath. These convection cells churned and created funnels of magnetic energy above the surface. Scientists concluded that these switchbacks form inside these funnels before rising into the corona and beyond. This is only one piece of the puzzle. However, scientists still don't yet know how they form. Over the next few years, Parker will keep looking for clues as it explores our sun up close. The sun is the only star we can study like this. It is also the only star we know that supports life on at least one of its orbiting planets. Understanding it is critical as we search for life beyond our solar system.
That will link directly into the question, are we alone in this universe? And that is one of the biggest questions for humanity to answer.
Artemis, the sister of Apollo. She will soon be returning humans to the moon. The decades of development are nearly complete. New hardware, new ways of making the journey, and new goals have been set. This time, the United States will not be going it alone. This time, it's an international effort. The first major test will be Artemis 1, an uncrewed journey to the Moon and beyond, a final hardware shakedown for manned flights.
Nowadays, astronauts, engineers and scientists are very excited to go to the moon because it's pure exploration. It's discovering terra incognita. We would go to regions that were never been, well, explored by a human, neither robotically nor in person. The moon is really our eighth continent, and it's there to be discovered. Last time humans have been there was in the 60s and 70s, and they covered, well, 12 people covered 6 landing sites, and imagine that in an area that's so huge. It really doesn't give us a lot of knowledge about the moon itself.
2, 1.
This lunar spacecraft comprises ESA's ESM and NASA's Orion crew capsule. It will be used for an uncrewed certification flight, performing a 6-day orbit around the moon.
We returned to the moon for various reasons, different technologies, and it is a big achievement, I believe.
All over in Europe, we have companies in 10 countries helping to put this ESM together, which is quite significant. And actually, there are hundreds and thousands of people working within Airbus, but also in our partner companies, to make this endeavor a successful mission.
Monitoring of the performance of the ESA segment will be conducted here at ESTEC in the Netherlands.
And that one is only on one side.
These folks here are specifically taking care of the European Service Module, which provides the human capsule part of that with all of its power and life support. So this team here is really taking care of the crew that'll be going to the moon and beyond.
So there are mainly 2 types of support. That's basically 2 types of situation. Nominal situation, everything goes fine. Here we are actively supporting, actively monitoring the spacecraft, looking at the trend of the parameters to try to predict as much as we can if something is, if a failure is building up or if everything is nominal. And again, anticipation is the key, meaning that you have to know your mission and you have to know what's coming up, what's coming next, for instance, if it's, and then things you cannot predict, and that's why we are training with failures in the simulations. These are failures. And to failures, how we react, how we talk on the voice loops, how we communicate throughout the position between the various subsystems to quickly identify what is the failures, to investigate it, to understand the root cause, and also any likely impact onto the other subsystems, on the system, and also on the mission.
It's human space flight, and you're always going to have anomalies. We don't say a problem. A problem is indicative of something you don't know that, but anomalies come from in engineering. You can find them, solve them, and continue on. And that's what the teams have been working through recently through the wet dress rehearsals. There was 4 dress rehearsals to make sure everything's absolutely right.
Anyway, you can do like this. Yeah, you can. If you click sheet.
Today's simulation is what they call an inspection simulation. So the idea is during a launch, they will do a systematic inspection of the entire spacecraft. The European Service Module sits on top of the NASA SLS rocket. So basically, on a pre-launch check, they'll just really systematically look at every piece of those vehicles, trying to identify any potential anomalies or such before they fly.
The surface of the moon has about the same area as Africa, and we only visited the moon 6 times in the 1960s and 1970s. So if you think about landing in 6 different spots in Africa, you quickly realize that there's so much more left to learn and understand about how the moon formed and how it's evolved over the last 4.5 billion years.
Before NASA's Artemis astronauts go to the moon, a small spacecraft called Capstone is leading the way. This small spacecraft will test a unique lunar orbit that has never been flown before. This orbit will be home for NASA's Gateway elements.
Behind me is a mock-up of the Habitat and Logistics Outpost, or as we call it, the HALO module. The HALO module and the power and propulsion element will be delivered to lunar orbit to make up the first components of NASA's Gateway. The Gateway is going to be crew-tended, where crews will visit the Gateway for a period of a few weeks or a few months. HALO and the PPE are just the first components of the Gateway, with plenty of room for future growth. Northrop Grumman has been delivering cargo to the International Space Station using the Cygnus spacecraft since 2013. That's 15 missions and counting. We are now using that Cygnus experience and our lessons learned in the design of the HALO module.
With the power and HALO modules in place, the Gateway will be built up over several launches. The IHAB module will be delivered by the first manned Orion mission. A logistics module with the Canadian robotic arm will be next. The lunar landing system, then Artemis 3, will deliver the refueling infrastructure and telecommunications module before proceeding on to a landing at the lunar southern pole. Before any descent attempt, a crucial component for Artemis is location of a landing site. Unlike the Apollo missions that landed along the relatively flat equatorial regions, Artemis will be landing at the southern pole of the moon, a far more challenging landing scenario. Six landing regions have been identified, close to the permanently shadow regions where water may be found. However, further exploration of these sites is required to pinpoint the most ideal landing location. This will require the services of robots. NASA is sending Viper to scout the terrain.
Viper is a rover of many firsts. First NASA rover to map water resources, and it's the first rover to wear a headlight.
Viper will be one of many robots descending on the lunar pole in search of water. Testing these robots is well underway in terrain most lunar-like.
Traditionally, rovers are operated from the Earth. With the Lunar Gateway being put in place around the Moon, there's the possibility of controlling them directly with much smaller time delay. And this opens up for new possibilities for things that you simply cannot do or is much more difficult to do from the Earth. So now we're here in Sicily. We're repeating our experiments on the slopes of Mount Etna. The astronaut is not on the International Space Station. He's controlling from a hotel room here. We have our European Space Operations Center in Germany, in Darmstadt, who are directly overseeing and running the operations. And in the role play, they are pretending to be on the moon, and it's very realistic because the slopes of Mount Etna is a wonderful lunar analog. It looks exactly like the moon. There's beautiful craters, there's rocks, it's grey. So we have the European Space Operations Center able to really immerse themselves in the role play, feel like they are planning traverses and exploring regions of interest on the moon, in close discussion with the scientists who also get this full immersion where they see a realistic lunar-like geology, so they can have a real discussion. They need to then communicate this to the European Space Operations Center, who has to then make decisions about how they are going to execute operations, whether they make use of the astronaut for direct teleoperation with a short time delay, or whether they make use of their own tools for planning longer traverses and not wasting astronaut time on this. So this is the type of trade-offs and the sort of things that we want to learn how to do for real when we go to the moon, by playing essentially the scenario, playing the game here on Mount Etna. The astronaut is doing the same as he did on the International Space Station in 2019. So he has a control station which allows him to fully teleoperate the rover. What I mean by that is that he can drive it, he can control the arms with the direct feedback. So we have a very immersive control station which allows him to feel a bit like he's on the surface. The robot is his avatar on the surface. It's designed so that he can touch things with the robotic arm and feel what the robotic arm feels. It's designed so that he can decide whether he wants to drive with the joystick, or he can plan his traverses and automatically do it. He can choose whether he wants to manually pick up rocks, whether he can do it automatically. And we really want to learn from his experience which of these tools he is using, which of these tools he is finding useful in different situations, and how his interactions are happening with the science team, how easy it is to communicate which samples to pick up, how the interactions are going with the European Space Operations Center, when they think it's better that he uses his tools to do it, or when it's better that they do it, how the handovers are working. All of these things is what we're trying to learn here. It's a very complex experiment because it has a lot of stakeholders, a lot of partners, because there's a lot of different objectives. We are trying to validate technologies that have not really been used extensively in space. We have this device we used in 2019. It's the first time something like at this level of complexity has been used to control robots from the space station. We have the whole operational scenario, which involves a lot of parties, this game, which is we're trying to learn a lot from. So this complexity makes it a very challenging experiment, but that way we learn a lot.
We are here at Mount Etna in the frame of the Arches campaign, and this campaign is organized by the German Aerospace Center. So there are multiple robots from the German Aerospace Center, via guests, our robot from ESA, and also other research institutes are actually practicing with their robots how it is on a real scenario. So here on Mount Etna, it is very close to what we expect on the moon in sense of soil conditions and harsh environment, dusty, rocky slopes and loose sand. Our robot is controlled today by an astronaut. For this purpose we invited Thomas Reiter. And for us it's important that's an astronaut, because in these scenarios we want to practice what happens in reality. So there would be an astronaut sitting in the spacecraft and controlling a robot on the surface of a planet. And in the past we have done this with the ISS. So we had Luca Parmitano in 2019 with Analog 1, controlling our robot in a hangar in Falkenberg. And here, of course, we are on Mount Etna, moon-like scenario, but it's very difficult to have an astronaut on the ISS controlling a robot here on the mountain, to have all the logistics and everything set up at the same time. But to have a fair comparison, we indeed have Thomas Reiter, in the hotel room in Catania, controlling a robot here in a realistic scenario.
Yeah, today was a very special scenario because we tested the cooperation between a ground control, people who are sitting in a control room somewhere on Earth, and the crew that is orbiting around the moon in the Lunar Gateway. And this specific cooperation turned out to be extremely fruitful. In earlier times, it was always thought that there is either a purely robotic operation, which is exclusively controlled from control centers on the Earth, and the crew doing something in situ, being really on the surface of the moon. And I think what we learn here is that this kind of collaboration that you are doing from ground control on the Earth, a crew that is on board a space station that is orbiting the moon, and a rover that is on the surface, can be extremely efficient and much more efficient than actually if either one does it alone. Well, it's certainly less dangerous to send a rover to the surface than to send an astronaut. It's also cheaper. It's also possible to not take up so much of their time. You know, astronaut time is extremely valuable, so you can send a rover to the surface. You can let the ground team do all their planning, let them do all the longer traverses, and you get the astronaut involved when it's necessary for maybe the more complex task or the things where he really direct teleoperation, direct control of the robot is more helpful.
Our rover is built by the lab and it's a demonstration rover. So we want indeed to figure out what features do we need in a future space mission. So of course, if you control a rover, you need for awareness video cameras for the simple ones. But of course, to go somewhere, you need a locomotion platform, and it needs to be fitted for this loose soil underground. And to manipulate things, for example, pick up rocks or maybe later maintenance of infrastructure, you need robotic arms. And so our robot was constructed with this purpose in mind, to have it controlled by an astronaut with force feedback to perform this kind of tasks. But of course, we are also looking in the future, so direct teleoperation is good. But of course, we also want to enhance our system by more and more autonomous features. And so there, my team developed, for example, automated rock detection, so that the astronaut doesn't need to grasp the rock manually, but indeed that the machine learning algorithm detects the rock, controls the robot to grasp it automatically. And this way, we want to step-by-step increase the capabilities to automated driving, automatic obstacle detection, rock detection, to come actually from a remote operated system to a more autonomous system. Today we try to achieve a full control and a full scenario of our robot. So in the past experiments we went always step by step. So we had a force feedback device on the station, we had a robot in a controlled environment, and indeed this is one of the first times we put out the robot in a really harsh environment here on Mount Etna. So it's moon-like, we have a complex scenario with the operations center in the background, the astronaut with time delay in the control center, and indeed a task that has been prepared by the team in Darmstadt that was not known to the scientists and to the astronaut beforehand. So here we really try to get as close as possible to real scenarios with surprises in a hard environment. And if we master this, we are really confident that these technologies can be developed further to make it space grade, to indeed be part of the next moon mission.
In our scenario, which is based on a notional mission, based on the European Large Logistic Lander, the astronaut, in collaboration with the European Space Operations Center, will be collecting the samples, bringing them back to the lander, and then they will be brought back to the gateway or directly to Earth for analysis by the scientists.
Autonomous robotics will be used not just on the Moon, but farther afield. Plans are underway with the Mars Sample Return mission. Landers and launchers are being developed for this mission that will see an autonomous robot, or even perhaps helicopters, that will land on Mars and pick up the samples collected by the Mars rover. Once brought back to the lander, they will be loaded onto a launcher, returned to orbit, collected by the orbiting vehicle, and carried back to Earth via a small re-entry vehicle holding the precious cargo.